Thanks everybody for coming. So as I said at the beginning, the way I organized the talk was to have it turned out to be 2.5 talks about sort of the developing the structure of the way that we in computability theory organize the study of definability, at least in the realm of what's absolute, sitting inside signal 1-2 definability. And then some comments about whether you could do it a different way. Is this particular way that we really think out intrinsic? And then 2 talks about how ideas from computability theory connect with other branches of math, or how to see it in sort of in action. Okay, so we're starting basically a new topic today. So if you were really interested in the things I was saying yesterday, well, sorry about that. And if you weren't interested in, you had already, retreated to the privacy of your own mind, thinking, well, I don't have to pay attention to what he's saying now because it's not relevant to me. Well, sorry about that too. So today, computability, randomness, Diophantine approximation. So the computability theory, or the study of definability, can be used to investigate almost any part of math. But what does computability theory, broadly interpreted, what's the perspective? Well, it's a kind of perspective of definability, which is also part of logic at large. It's you have some mathematical situation, you have some collection of methods or principles of proof, or you have the stuff that you are using to understand some situation. And then you can ask, what's the scope of those methods? Right? Can the methods I'm using capture what's going on there, or is it too complicated to parse using the methods that I'm employing? Right? Or there's some kind of phenomena there. Can I calibrate the way that business behaves according to the complexity of definability? And computability is a particularly nice, natural boundary between one kind of behavior and another, but there's also several others, as we saw, several other landmarks there. Okay, so I want to do that today with randomness. And so randomness is a primitive. There's no way that you're going to ever completely explain what randomness means. But I think you can look at randomness from all sorts of perspectives. In the computability theoretic perspective, gives some insight into it that is particular to this point of view. Okay, so let's see. So if you look at the title, there's some things here that don't typically appear in the same phrase, right? Computability, randomness, and Diophantine approximation. Usually you don't see those 3 topics uttered in the same phrase. The study of Diophantine approximation is I guess, part of analytic number theory. Right? And usually you don't see computability and analytic number theory in the same breath. But we're going to try. So why? Why would it seem natural? Well, in recursion theory, you investigate asymptotic properties of some subset of the natural numbers. You could say it's computable. You could look at, as we will, about it's random with respect to certain definable aspects. The initial segments are easy to describe or difficult to describe. Okay. And we looked at what does it mean to compute something? What does it mean to write something as a limit? That was 0 prime can compute things that are recursive limits, or Boolean soup, or things. Those are aspects of approximation. And you can calibrate the complexity of the objects that can be approximated. Okay, Diophantine approximation investigates finite approximations to a real, and C now is a real. It's something sitting inside the real line. And you try to approximate a real number by rational numbers. And you can look at things like what are the asymptotics of such an approximation? So things that come up in that context are, is it normal? If you look at it in base B, right? Do you see that you look at its base B expansion, and ask, does every base B word of digits occur with what you would think would be the expected value? If the word has length n, you would expect that word would appear, 1 over b to the n times. Like if it's in binary, it would asymptotically have the same frequency of zeros as it has frequency of ones. That's simple normality in base 2. Okay, so that's one kind of asymptotic property, and that has to do with approximating the real by b-adic rationals. Then there's other things like, is it a Liouville number? So a Liouville number is one that's very well approximated by rationals. We'll say more about that. And there's various other questions that one can ask about a real number vis-a-vis the way that it's approximated by rationals. Okay, so I think these two, as presented, these two, like threads of interest are not that far apart. They have a lot in common conceptually. You can use rational numbers to approximate real numbers. You can use algorithmic methods to try to specify real numbers. Right? There are some similar questions and crossover of interests. Okay, so let me talk about computability and randomness. Now you could, in a different talk, instead of talking about randomness as an aspect of measure, right? You could also talk about computability and genericity, where genericity is a matter of category. Right? So recursion theoretically, you can look at what happens for generic reals. Recursion theoretically, you can look at what happens for random reals. There's a duality between a set has full measure and all of its elements are random. So how can you use computability theoretic thinking to calibrate randomness? Okay, so a little bit about that. Okay, so if you want to say a real is effectively random, one way to put it together would be to say, well, it doesn't belong to any really concretely specified null set. And so a real is supposed to be random if it doesn't have any kind of measure zero behavior. And so, of course, every real is unique, right? And it belongs to the set in which it is a singleton. That's a null set. Right? So it's very hard to say any particular real is random, but you could say that a real is random with regard to these criteria. And that's the game here. Okay, so this goes back, I think, to the 70s. A pair of Martin-Luft test is a uniformly, it's a way to specify that a real doesn't belong to an effectively presented null set. Okay, so it's a little complicated to write it, but we're really saying that an effectively random sequence avoids every effectively presented null G delta. Okay. So how do you effectively present a null G delta? You take a uniformly computably enumerable sequence of finite sequences. We're working in 2 to the n, so a basic open set is specified by a finite sequence. It's all the x that extend sigma, where sigma is some finite binary sequence. That's a basic open set. An open set is a union of basic open sets. So an open set is specified by a countable collection of finite sequences. Okay. So you look at a uniformly computably enumerable sequence of subsets of 2 to the less than omega, or less than n. So that's specifying a countable sequence of open sets. Right? If you have a collection of finite sequences, the open set of reals that extend some sequence from that set is specified by the finite sequences in the set. Okay, so a collection of finite sequences specifies a collection of basic open sets. The union of that collection is an open set. Okay, so we have computably enumerable specifications of open sets such that their measures are uniformly of the open set specified, going uniformly to 0. So the computably enumerable this open set, then you have an open set whose measure is half, and then an open set whose measure is a fourth, and so forth. And those open sets are specified algorithmically. Okay, then, a set is Martin-Wolf random if for every such Martin-Wolf test, X is not in the intersection. So it avoids, so you have an effectively presented intersection of open sets. X looks random if, and the open sets have shrinking measures. So you have an effectively presented G delta of measure 0, and X looks random if it's not an element of the intersection, not an element of that G delta set. Yeah, go ahead.
Is there any reason to consider Mn that are not like nested?
No, you can, I'll say, you can assume that they're nested.
Okay.
In fact, not only can you assume that they're nested, there's a universal test that comes out of the universal sigma 0, 1 predicate. So you can prove that there's just one, you don't have to avoid them all, there's one test that rules them all in the arguments. Yes, there's just one effectively presented null G delta. Right? If you're not in that set, then you are what's called one random.
Wait, is passing avoiding the set?
Yeah, passing means you're not in the.
Oh, okay.
You pass the test means you look random. Okay. All right. And that's the vocabulary people use. Okay, so that's one way to specify you look random with regard to things that are effectively presented. Okay. Example. If you have a recursive set, it's not one random. Right? Because you can just, this is recursive, I can just talk about the sequence of its initial segments. So you just have a sequence of open balls. The intersection of that sequence of open balls is the singleton X. Okay, so it fails the test of not being itself. Okay, so there is a one random recursive in 0 prime. So the halting problem is sufficient to cook up a real that looks random for all of those effective Markov tests. We'll see an example in a minute. Okay, so now there is a second. So there is a second way to try to identify randomness. The first example that I gave to talk about effective notion of randomness is to say, well, a random real doesn't exhibit a measure 0 property. So look at all the effectively described measure 0 properties, and say you're one random if you don't belong to any of those null sets. So it looks like it doesn't belong to a measure 0, doesn't have a measure 0 property. A second aspect of randomness is the one that usually comes up when you're trying to informally describe what would a random binary sequence be. Well, flip a coin, flip a fair coin, and choose the digits according to the outcome of that. Choose the digits at random. And the sequence you get will be a random infinite sequence. Right? And then you can apply things like the law of large numbers, and the asymptote will be simply normal in base 2 because of the law of large numbers. Okay, so that sort of thing is looking at the bits of the sequence and saying that something about the bits of the sequence, right, is determining that it's random in the end. So that's where this attempt to define randomness originates. So this is randomness by Kolmogorov complexity. So asymptotically, you could say, an effectively random sequence has initial segments with dense information. In other words, what does it mean to say that that's the, computationally, what does it mean to say that a sequence of n bits, right, has information that's sort of n, that has size n? Well, you have to measure what's the information content of a finite sequence. One way to try to do that computationally would be to say, how hard is it to define that sequence? How hard is it to build that sequence up? What's the measure of hard? what's the shortest algorithm that you can use to generate that sequence? So computationally, how hard is it to specify this sequence of length 1,000? Well, take the shortest program, which when you run that program, it outputs that sequence. And look at the length. So that's a measure of how many bits you need, right, to specify that sequence. Because that's the Kolmogorov complexity approach, that a sequence is random if the only way to really to describe the sequence is just to tell you what all the bits are. If you were going to do this fair coin thing, there's no way that, and you want to bet on how it turns out after 100 flips. There's no way that you're gonna like figure it out. I know with probabilities, 0.75, it's going to be such and such sequence. But it's not like that. Okay, so here's the way to do this kind of initial segments of dense information and set it up as a definition of what it means to be random. This is due independently to Chaitin and Lennon. Yeah, I was told any theorem that's ever proven was proven earlier in Russia. So this is such a case, independent lines. Okay, so if F is a partial map from finite sequences to finite sequences, it's said to be prefix-free if its domain is an anti-chain. So if F is defined on sigma, it doesn't take extra value. If you're computing, okay, that's just a definition. All right, so now, so if F is defined on sigma, it's not defined in any proper extension of sigma. Okay, the F complexity is written as H sub F of a sequence tau is the least length of a sigma such that F of sigma is equal to tau. So you can think of F as the operating system, sigma is the program, and F of sigma, you run the program, you output tau. Okay, prefix computable function U is universal. So this is a function from finite sequences to finite sequences. It's universal if the value, I forgot the C. There should be a, I got this completely. Oh, the prefix U is universal if there is a constant such that this is less than or equal to this plus C. So with a little bit of cost, with a constant cost, you can simulate F. Okay, and there is a universal machine, and typically you forget about, you identify all the universal. An additive constant doesn't really mean much when you're talking about complexity, much bigger than the constant. Okay, so you fix a universal U and let H denote HU, and that gives you a kind of notion of complexity of finite sequences. And it makes rigorous the notion of the shortest program that computes some sequence. Okay, and then the theorem is that these two aspects of randomness coincide to identify the same family of binary sequences as random. So a sequence is random, an infinite sequence is one random, or effectively random, if and only if there's a constant C such that for every length L, the initial segment of X of length L has complexity greater than or equal to L minus C. Okay, so up to an additive constant, the information in the initial segments of L, right, has size L. So you can't, like, there's no patterns that let you predict, like every other digit is a 0, so I only have to specify half the digits. There's nothing like that. That's the sort of Kolmogorov complexity view of randomness, and that corresponds exactly to this measured theoretic view of randomness. Okay, so that's, yeah, go ahead.
Wait, what is this H down here, HU?
It's, yeah, let H denote HU.
Oh, yeah, okay.
Yeah, so you fix one because the additive constant gets absorbed in the theorem anyway. Okay, so there's a from the point of view of, usually when you see conceptually different conceptual motivations ending up with the same constant, with the same interpretations, syntactically different or conceptually different ways to capture some aspect of a phenomena, and they capture exactly the same sets. That's some evidence that, you know, you hit something, you found something. Intrinsic.
One random again?
Well, yeah, so one random was this: you avoid every effective represented G delta, null G delta. And then this other random is that the initial segments are incompressible, computationally incompressible. And those capture exactly the same sequences. They identify the same sequences as being random. Okay. All right, so that's a nice. So in this context, you can talk about let X be random, right? And let X be random has a very precise meaning, right? And it's this. It can be one random, and the one randoms have some interesting statistical properties of randomness, but one is not big enough for certain other aspects of randomness. And there's a nice theory there that lets you distinguish how much randomness do you need in order to do various kinds of almost everywhere arguments. So you can calibrate degrees of randomness according to, well, what are you allowed to use when you compute H? Or what are you allowed to use when you put together Martin-Loeb tests? They don't have to be computably enumerable, they could be arithmetic, or calibrate the notion according to definability, and you get an induced calibration of the aspects of randomness. Okay, so that's a sort of computability theoretic spotlight on the notion of randomness. And then, how about some examples? This particular one was known as Chaitin's omega, and here's the definition. So choose this universal prefix-free computable function. So remember, its domain is an anti-chain. Capital omega, this depends on which U you get. Capital omega is the sum of it's the measure. It's the measure of the open set determined by the domain of U. And so U is defined on its domain as an anti-chain of sequences. A sequence has length n. The measure of the open set that it determines is 1 over 2 to, the sequence has length n. It determines a ball. That ball has a measure 1 over 2 to the n. Omega is the sum of the measures of the domain of that universal function. Okay? And because in Cantor said according to the measure that a sequence has measure 1 over 2 to its length, omega has to be less than or equal to 1. Okay, and then we'll identify omega with its binary representation. And Chaitin proved that omega is a one random real. Okay, so it's a nice layup. You can approximate omega. You just watch the domain of U grow as you see more and more programs halt. Right? You add more and more to the approximation to omega, because the domain is a computably enumerable set. It's the domain of a partial recursive function. Okay, so it's a computably enumerable set, and you can approximate it monotonically. Right? So that means it's computable from 0 prime, right? Because 0 prime can evaluate computable limits. So this is a real number that 0 prime can approximate this number. Can give you a Cauchy sequence. 0 prime can compute a Cauchy sequence that converges to omega. No recursive thing can be one random. So here's something recursive in 0 prime. And as I said, the approximation to omega is monotonic. So what do you think the Turing degree of omega is?
Can it also go the other way? If you
Yes,
have
you got it. That's right. So omega is something that's equally computable with 0 prime. You might hope, like, oh wow, I could take a kind of nice random. It looks random, right? And random things are supposed to have no information. They're just static. In fact, there's a nice theorem independently due to several authors, one of whom was my thesis advisor, Gerald Sachs. And Sachs and the others. Yeah, I don't want to put the fact that I don't know any of the other authors' names on Sachs himself. That's my problem. Suppose that you have a real number that's computable relative to a random input. Then it's computable. But you need more randomness than one random. Because 0 prime is computable from this random number. All right, so there is a nice example. It comes out of a universal object. Okay. Now, there's a third in the realm of reals that are recursive in 0 prime, right? Or reals that can be approximated. There's a third aspect of randomness, and it comes out of this suppose out of this definition. Suppose that you have two sequences. And let's say, so they are monotonically increasing computable sequences of binary strings. And by monotonically increasing, I mean we have these finite sequences of binary strings. They correspond to dyadic rationals. And those rational numbers are increasing. So the sequences are increasing lexicographically. So I suppose you have a sequence of dyadic rationals, A vector and B vector, and they're monotonically, and they're computable, and they're monotonically increasing. They're bounded by 1. They converge to alpha and beta. Okay. Then you say that A dominates B if there's a positive constant, such that the modulo a multiplicative constant, the rate at which A converges to alpha is slower than the rate at which B converges to beta. And so, right, the distance, modulo this multiplicative constant, the distance between AI and the limit, alpha, right, is greater than the distance between BI and the limit beta. Okay, so the A's are going to alpha no faster than the rate at which the B's are going to beta. Okay, so it's a convergence domination. Okay, so A dominates B. This ordering is due to solving. So A dominates B if there's a positive. If the A's are converging no faster than the B's. A vector is said to be universal if it dominates every such sequence. Right? So it is the slowest converging recursive, monotonically converging recursive sequence. And a real is said to be omega-like if it's the limit of such a universal sequence. And no surprise, omega is omega-like. Okay, so omega is an example of a random real, has the property that it is as difficult to approximate as any approximable real. Is that something else you would think about? Something that's random. Something that's random, there shouldn't be like a really fast way to converge to something random. Right? The random thing is glitchy. It's hard to predict. It's hard to approximate. Okay, and then the theorem is that being universally hard to approximate among the monotonically approximated reals, being universally difficult to approximate is another characterization of randomness. So a random real is one that avoids null sets. It is one whose initial segments are hard to describe. And among those sort of concrete randoms, the one randoms that are approximable recursively, it is a random real is one that is maximally difficult to approximate. Yeah, go ahead.
I mean, just by definition, it means that there's one sequence which approximates it poorly, right? I mean, you said it's difficult.
It dominates every such sequence.
Yeah, but this means
that's what happens is that any sequence that can approximate alpha is dominated. That's right. But if they're not random, it's okay. Good. So that's the theorem. Yeah. So randomness has different aspects, and they all sort of cohere if you sort of calibrate them definably. Okay. Okay, so now, now that there's the typical, I forgot what his name is here, until I had remembered it. Okay, so the typical way to, you can easily, it's often the case, and it depends on the problem that you're looking at. It's often the case that sometimes it's convenient to talk about a set of full measure, and sometimes it's convenient to talk about a random real. Right? And typically randomness is, those things, like, that's the way probability works. Right? That there's a duality between what happens almost everywhere and what happens for a random sample. And here's a precise version of that statement. This is not true to me. I first heard, I don't know where it's lost to me in the mists of time, who first observed this. I heard it from you, Leanne. That's the first time I heard it. So suppose that you have a pi01 class. So it's a set of sequences that satisfy for all n, something happens for the first n bits of x. Then the following are equivalent. C has positive measure, or C has an element that's one random. So it's a quantitative version of the duality between something happens on a set of positive measure, something happens at a random point. And now random, well, we know what random means, right? So, and this also scales. So it gives you a nice sort of apparatus to move between one perspective and the other, as is convenient. Okay. And then that doesn't apply only to pi01 classes. It's by the principle of relativization. In fact, it works this way. Suppose, if you have an arbitrary set, right, then the following are equivalent. It has positive measure. And so now there's no effectiveness here. This is just this arbitrary set of positive measure. And the second one is, for every x, A has an element that's one random relative to x. And so a set has positive measure if and only if, from the computational point of view relativized, it has random elements. For every x, there's an element of A that is one random relative to x. And the proof of this is, well, if A has positive measure, it has a closed subset of positive measure. So you might as well assume A is closed. Right? And then relativize that fact up there, and you're done. So there is, even when you're not restricting your attention to just definable sets of readings, you still get an insight, this insight between having positive measure and also having random elements. And now random means, well, you have to have elements that look random no matter what, from what perspective. Okay, so that's a brief history of the really theoretic approach to randomness. Now I want to do this. I want to look with the same sorts of questions in the realm of Diophantine approximation. So let's see what I mean by that. Okay, so we're going to talk about the analog, what I think of as being an analog of Martin randomness or measure theoretically based randomness is this notion of normal. Okay, so let C be a real number. C is simply normal to base B if in its base B expansion, which I'm writing as C sub B, each digit occurs with limiting frequency equal to 1 over B. So that's simple normality. So the real number 0.101010 ad infinitum, right, is simply normal in base 2. Because each digit occurs asymptotically with frequency 1/2. Okay, C is normal in base B means every finite pattern of the numbers from 0 to B minus 1 occurs with limiting frequency equal to its expected value. And so that's what I was talking about, normal in base. So simply normal is simply looking at the digits. Normal in base B is looking at all blocks of digits. And C is absolutely normal, right, if it's normal in every base B, and it turns out that that is equivalent to saying it's simply normal in every base B as well. Okay, so those are degrees of normality. Okay, so the first example, and this is early on in the beginnings of the early days of the development of measure theory. Borel proved almost all real numbers are absolutely normal, and that's this is at the same time, right, as the law of large numbers was being formulated and proven. This is an instance of the law of large numbers. Okay, and in fact, any one random real is normal. But there are, well, I'll save that for a second. Okay, so Borel posed the question. This was early, I don't know. This question was maybe the early 1900s. Give an example of an absolutely normal number. They exist because they have full measure. But how about, you showed me many, show me one. That was the problem, right? But give an example of an absolutely normal number. And by that I think he meant that, one of the mathematical constants. So something that's, it's an example that I've already seen in some other context, like pi, or E, or something, something that came out of geometry or analysis or something. Even better if it comes out of physics, I think. That reminds me of an incident that happened to me when I was an undergraduate. When I was an undergraduate, I was not a math major, I was a physics major. And so, but I thought I was hot stuff. So I wanted to take all the physics classes. So I was taking the graduate physics class, the mathematical physics. Okay. And the whole development, interestingly enough, was all like take an infinitesimal surface element and look at the normal vector, an infinitesimal normal, and then end up proving some kind of divergence theorem or things like that. So the whole class goes like that, and then we get to the end of the class, and the professor held a review session, and people asked questions about the homework and such. And then, any more questions? There were no more questions. So, are you sure? That's like we still have time in the review session. So then I raised my hand. I do have a question. Oh, okay, what's your question? And I said, so I understand the way that the arguments go, but what exactly is an infinitesimal surface element? So he paused and he looked at me. And then he gave what I thought was, at the time, the perfect answer. He said, stop that. Perfect physics answer. Stop that. You're going to scare the other students. Oh. Okay, so give an example of an absolutely normal number. did he mean by that example? Okay, so now, in the 50s, after Roth's theorem about evidence was accumulating that irrational algebraic numbers look random. They have some of the features of randomness in terms of Diophantine approximation. So Borel conjectured in the 50s that irrational algebraic numbers are absolutely normal. And to date, there is no progress in this conjecture. It is not known whether it's true or false for any irrational number. Yeah, go ahead.
So the fact that one randomness implies normality, does that sort of encapsulate the fact that if you're not normal, there's some subsequence that doesn't appear as often as a coin?
There's a bias.
Yeah, there's a bias, so then that makes it less normal?
Infinitely
or
often.
less random?
Infinitely often there's
Yes.
a bias. So infinitely often there are segments which can be compressed.
So if you're trying to guess it, you'd have a little bit of that bias in your favor.
That's
Okay.
right. Okay, so completely open. Square root of 2, who knows? I think this is a good example of the if you're a logician, you tend to think of numbers and their representations as interchangeable. Right? A number is something I can, a number is what? It's 3.14, blah, blah, blah. Right? We don't think, oh, it's the ratio of the length of the circumference over the diameter. We think of it as, but there's a big gap, which is sometimes hard to bridge, right, between the properties of the number algebraically or geometrically and the way we represent it. So it's a surprisingly elementary question. It seems quite intractable. All right, so examples. So Champernon in the 30s gave this example. Since we're just writing down the digits in base 10 and the numbers in base 10 representation of the natural numbers and concatenating them to get a number, 1, 2, 3, 4, 10, 11, 12, etc. That's normal to base 10. It's open whether it's normal in any other base. And it's like I said, it's an elementary but intricate combination to show it's normal in base 10. The first constructions, or the first kind of specific examples of absolutely normal numbers were produced by Lebesgue and Sierpinski. And what did they do? They came up with they came up with a nice definable closed set, bounded. They gave an example, a nicely defined, bounded, closed set, all whose elements are absolutely normal. And then they defined the least element. And so it wasn't an example in the sense of, it's not an example like pi, but it is an explicit definition of an absolutely normal number. Yeah, so in those days, there wasn't that much difference between one field and another. Then Turing showed that there's a computable absolutely normal number. That was in the 30s. So and he, I think this is remarkably prescient. He gave an algorithm to compute the digits of an absolutely normal number, but he remarked in the margins, right, that nobody's ever going to run this algorithm. It's going to be too slow. There's a sort of triple exponential time look ahead, or you have to look ahead as to what's going to happen before you can decide what your digit is going to be. So it's a quite slowly running algorithm. But other examples were Schmidt gave one. I should have written down. Knuth gave one. Becher and Figueroa. There was a sort of missing point in Turing's argument, and they filled it in. So there's different notions. There are different ways to come at algorithms to produce absolutely normal numbers. That raised the question of, is there a feasible algorithm? Is there an algorithm where you can actually run it and see the digits appear across the screen? And Becher, Heiger, and I gave an algorithm that worked in essentially quadratic time. And then there were other, this algorithm was direct construction on Watson and Ardomo, and independently Pagela and Nice gave other arguments for to produce absolutely normal numbers in polynomial time. And the way they did it was they looked at polynomial time versions of one randomness. Right? No, randomness can also be formulated. At the level of one random, I think it's kind of awkward. But randomness can also be, so sort of in the way you were saying when you were talking about not random. You can also describe randomness in terms of you can't win money in a betting strategy against a random payoff set. Okay, so that aspect of randomness ported to polynomial time leads to a construction of a polynomial time construction of an absolutely random real. Okay. Okay, so the proof, though, that my favorite proof, right, is it's a recursion theoretic construction. It's what you might think of as a kind of construction of it's a finite extension. We say these many bits, and then we say those many bits, and those many bits. You keep appending the bits in a computational way. Okay, and choosing what to do next relies on a counting argument, which is in Hardy Wright's book. All right. Okay. Yeah, go ahead.
So is there an actual computer program anyone has made to write down?
Yeah, there is. Yeah, I didn't put it up, but I could show you a picture where you get all the bits and you put it on a grid and it looks random. Yeah, I can show you another. Yeah, you can actually program it. The program's not that hard. Okay, so the next, so we're talking about randomness, and can we have something? So we saw it in the computational setting. If you think about this aspect of randomness or that aspect of randomness, and you formalize it, and then you prove, well, they identify the same. Those different notions of randomness identify the same sets as random. So we have an aspect of randomness, right, a characteristic of randomness, which is normality. But normality is talking about representations in a certain base. So we have a natural way to talk about random in this sense versus random in that sense. Right? If you're normal is a stand-in for randomness, and this sense could be in base 2, that sense could be in base 3, and another sense is base 5, etc. Base 6, base 10. Right? If you look random in one base, you have to look random in every base. Right? So is randomness is normality base independent. So that was a nice problem. I tried to remember this morning who posed that. I think maybe it was Steinhaus who asked that question. But it was, well, let's see. Right? So there's one aspect of normality in one base which is related to normality in another. Say that the two natural numbers are multiplicatively dependent if one is one's a rational. They're both powers to a common base. That's another way to say it. Okay, and if you have two numbers that are multiplicatively dependent, then normality with respect to one is the same as normality with respect to the other. If you're normal to base 4, you have to be normal to base 8, and conversely. Okay, so that's one connection between normal in one base versus normal in another. And then Wolfgang Schmidt proved that that's it. That's the only constraint. So if you let S be the set of numbers that are not perfect powers, then if you take any subset of S, there is a real that's normal to every base that's a power of an element of R. R is the subset. So you take some subset of S, call it R. There's a real that's normal to everything in R and not normal to anything that's not in R. Okay, so you can pick and choose right? For which bases are you going to look normal? And for which bases are you going to not look normal? Right? And the only constraint is this constraint of multiplicative dependence. Okay? And this was an extension of Cassell's, I think, if I remember right. It proved that if you take the Cantor middle third set and look at inside the reals, and you look at the measure, the usual measure that I just described on 2 big men, right, on that set, then almost every real in that set is normal to every base that's independent of 3. So if you're an element of the Cantor middle third set, your base 3 expansion omits the digit 1. Right? You either go to the 0 side or the 2 side, and you leave out the middle third, and all the way up. So an element of the Cantor middle third set can't be normal. It omits a digit in base 3. Right? But in every other base, right, a random element of the Cantor middle third set is normal. That's a special case of this thing. Okay, then, what sort of things does a recursion theorist do in trying to understand this kind of situation? Well, one thing that we do, right, is how complicated is the property of normality? If you look at normality as it's stated, for every base, for every word, the asymptotic, there is an L such that after L, right, the frequency of that word is, so for every base, for every epsilon greater than 0, there is a length of the base B expansion such that after that, the frequency count is less than epsilon off expected. Yes, that's what it means. That's a pi03 for all there exists for all. Property. And so you can analyze, well, is that optimal? Is the native definition, is there some simpler property which is equivalent, right, to normality? So that's a question that is a question about definability. Is there a simpler way to define normality? Something that this is the sort of things where good theorems are proven. You have something like every sequence has a convergent subsequence, and compare that to, so a sequence is convergent if there exists a real, right, and you converge to it. But a sequence is also convergent if it's Cauchy, which is an arithmetic property. Right? So, and that's a nice theorem. Okay, so, but in the case of normality, there is no simplification. Right? What the heck? Why am I looking at the wrong? No, I guess I did. Okay, so I guess I must have cut that slide out oh no, I wasted a lot of time after having cut that slide out of my talk. Or maybe it comes later. But in the invest, so you prove that this property of being absolutely normal is pi03. Now, in order to do that, you have to understand, just like in Hilbert's 10th problem, the property of being Diophantine is sigma 01 complete. Right? It's a Diophantine set is identified with a sigma 01 set. Right? So every sigma 01 set can be interpreted, right, as a Diophantine set. Diophantine definitions are fully expressive. To understand that, you have to understand, well, how do you witness this existential quantifier? How do you witness there exists a computation and express that in a Diophantine way? With normality and understanding its syntactic complexity, you have to do that for the alternation, for all there exists for all. You have to show that the satisfaction predicate for normality, right, is witnessed by quantifier, fully expressive. That making something normal can mimic the satisfaction of any pi03 phenomena. When you do that, right, you have to assert control of all the quantifiers. You have to know how, for all there exists, I have to know, well, for this guy, it's in my control whether there exists somebody for all. And so you have to have complete control of how to satisfy or deny the instance of normality. With that kind of control, you can do something like this. But let R be a pi03 subset of the bases. Then there's a real number C such that it's normal in every base in R, and not normal in any of the other elements of the set of bases. And furthermore, C is uniformly computable. Right? So you have complete computational control. You can build C. Right? And it's uniformly computable in the pi03 formula that defines R. So if you have a definable specification on the set of, and pi03 definable, not recursively specified. If you have a pi03 definable constraint on the basis for which you want to achieve normality, you can compute a real which is normal on exactly those bases. So you have, this is an analog, right, of saying that sigma 01 sets are Diophantine. Right? Now pi03 sets are base specified, normality base specified. So you can do whatever you want. So that says, corollary, the set of real numbers that are normal to some base, there exists a base to which they're normal, sigma 0 complete. Okay. Good. Normality is a pi03 property. That's what I mentioned earlier. I was deducing, I reversed the order of discovery on that. And I said, etc. Oh, so the one thing to comment here is that Schmidt's method was based on, it was a piece of analytic number theory. Right? It's based on sort of analytic estimates. And in order to get the kind of control you need for this situation, you have to make everything discrete. Right? Because you're computing with, computations are finite. Right? So you have to get all of these estimates and make them discrete and make them manipulatable. To get this kind of result. Okay, so now, what's the payoff? What's the payoff? What kind of payoff could you get? Right? When you take some business like normality, and you get the quantifier by quantifier, number by number control on whether that property is going to hold. Well, instead of looking at Schmidt's theorem, the Cassel-Schmidt's theorem had to do with normality. Normality talks about all words. Your normal in base B means every pattern occurs with its expected frequency. Simple normality only talks about digits. Okay. But you have complete control, word by word, step by step, Skolem function by Skolem function, right? To achieve or deny normality. The kind of theorem you might look for is, well, let's look at not normality, but simple normality and see what's true. See, how it works. So C is simply normal in base B. This is the reminder. Every digit occurs with limiting frequency 1 over B in the base B expansion of C. Okay. So to be simply normal and to analyze simple normality, right? For a number C, what are the properties of the bases such that C is simply normal for that base? So if we're looking at base S, real number and a real number C, if C is simply normal to base S to the K times M, then C is simply normal to base S to the M. So if you're normal in some power of a base, you're normal in that base. So like, for example, suppose that you have a number that's simply normal in base 2. Okay, so the digits in, base 4. Right? So the digits in base 4 are uniformly distributed. Okay, now when you write that number in base 2, what are you going to get? The digits, the base 2 expansions of the base 4 digits, 0, 0, 0, 1, 1, 0, 1, 1. Those digits, if you look at those 4 combinations, there are as many zeros as there are ones. So if you have as many, so 0, 1 and 1, 0, they're balanced already in base 2. But if you have as many 0, zeros as you have 1, 1s, well, then you're going to have as many zeros as 1s. So if you're simply normal in base 4, you have to be simply normal in base 2. Okay, and then that's the content here. Second, if there are infinitely many positive integers such that x is simply normal in base s to the m, then it's simply normal in all the powers of s. Yeah, go ahead.
The first bullet point, the converse fails spectacularly, right?
If you are, yes, right, as we saw,
1,
0,
1,
1, 0, 1, 0, 1.
Yeah, I can get it.
Right, that's right. Yes, this simply normal in base, good question. Simply normal in base 2 does not imply simply normal in base 4. So the question is, what are the conditions that are achievable relative to some number of z? So it can be simply normal in base 2 and not simply normal in base 4. And here's the theorem. Those conditions that I just mentioned are sufficient. They're necessary and they're sufficient. So if you have let m be a function, so m is telling you for each possible, the multiplicatively independent bases, m is telling you, to which powers of s you want to be normal. And m it has to have the property that if somebody is in the base s set, like if 4 is in the base 2 set, then so if, sorry, I said that wrong. If exponent 2, like 2 to the 2, is in m, then 1 has to also be in m. And so m is in m. These are the powers. M is a set of powers of the bases for each s sitting inside big S. So if s to the k is in, so is s. So that's this part. And secondly, if you have to be normal to infinitely many powers of s, then m of s has to be all the powers of s. Okay, so, okay? And then the theorem is, if m satisfies this property, it's specified, either you specify you are normal in base s, or you're normal to these finitely many bases, and it's not the case that, and if you're normal to s to the a, b, then you have to be normal to s to the a and normal to s to the b. Okay. Okay. If you have an m that looks like this, then you can find a real number, which is simply normal to exactly the powers of s that are specified by m, and to no others. And the proof is the same. If you know that m is computable, you can compute such a number. So the proof comes out of the hands-on analysis, quantifier by quantifier, of how to build a real and control the definable property of whether the real is normal to a base or fails to be normal to that base. Okay, and whereas the construction of a number that's absolutely normal rested on a sort of classical fact you can find in Harvey-Wright, this proof needs something more subtle. So I needed some we needed some combinatorial number theory, and I got a nice explanation of how combinatorial number theory works from Mark Heyman, who's a combinatorial number theorist. So it's an interesting, an investigation that's motivated by computational considerations, right? Retools the apparatus of controlling normality in different bases so as to be discrete and Skolomizable, but it ends up giving you, an extra apparatus to build things, which it doesn't come out, it's sort of naturally analytically. Okay. All right, so now I want to, in the last, what time is it? Do I end?
12:50.
I end at 12:50. Oh, okay. All right.
It's a good cutoff point, right?
Yeah. Okay.
Okay.
Do it again.
Any more quick questions?